Hi, my name is Ilan Levine. I am a professor of physics and astronomy at IU South Bend, and this is part two of our introduction to dark matter. In part one, we discussed the evidence that dark matter exists based on a wide array of astronomical observations. We concluded that most of the mass was not in the form of atoms. We also learned that this mass is invisible and only interacts with ordinary atoms very, very weakly. We discussed various techniques for hypothesizing the nature of dark matter, and were introduced to one particular favored hypothesis, the weakly interacting massive particle, or WIMP idea. We also learned that dark matter is all around us. It's going through our bodies, although we don't feel it, because dark matter interacts so very weakly with the atoms of our body. And yet, despite this, without dark matter, condensed systems made of atoms, such as stars, galaxies, us, wouldn't exist. But today, what we're going to talk about is how we're searching for individual bits of this dark matter. We know dark matter exists, but we don't have evidence for individual bits of the stuff. So there are three general techniques that astronomers and physicists use to search for this exotic matter. One technique is based on the hypothesis that dark matter has the nature that dark matter particles can annihilate with each other, creating high energy gamma rays. And they would be doing this at a higher rate at the center of the Milky Way galaxy than anywhere else. And so gamma ray telescopes have been put into space looking at the center of the Milky Way galaxy to see if there is a peak at some particular energy for gamma rays that might be coming from dark matter particle annihilations. Another technique is used by high energy experimental physicists who recreate the conditions of the early universe by smashing various nuclei together at very high energies and recreate the conditions that obtained when the universe was much less than a second old, the epoch when dark matter particles, in fact, would have been made. And what these physicists do is look for evidence of dark matter having been created in these collisions. The third technique, and the type that I'm involved in, is called the direct detection technique, where we set up a target of ordinary atoms for dark matter particles to scatter off of, and we search for evidence of nuclei which have been bumped by an unseen projectile. But the two collaborations that I'm working on are trying to detect this. The problem is that these collisions are very, very low energy. And so what we're looking for is the result of a low energy collision with a single nucleus, which is quite challenging. This can be further understood when we consider the wide array of possible probabilities for dark matter particles hitting atoms and the wide array of possible masses of the dark matter particles. The probabilities vary by 1,000 trillion parts, and the masses also vary by 1,000 trillion parts. And I guess you can understand this situation a little bit better with this analogy. Let's say you've got a garden that you know is being raided by some sort of pest, but you don't know if the pest is flying, crawling on the ground, or burrowing underground. Clearly, the type of trap you would use would be designed based on the type of pest that you believe is attacking your garden. And so you have to make the right guess. So obviously no one type of detector can be used to explore all possible natures of the pest, or in our case, the dark matter. And so we have to go with the kinds of guesses that we feel are the most likely. Okay, so let's look at this a little bit more closely. What we're looking at is single low energy nuclear recoils. That is, we have an incoming dark matter particle, scatters off of a nucleus, and then outgoing dark matter particle. We have not seen the dark matter particle, of course, it's invisible. The nucleus recoils at very low energies, and we need some sort of trick to turn this very small recoil energy into something that can be detected. The technique that my collaborators and I use are based on superheated liquids. Superheated liquids are liquids that are heated above their boiling temperature. But it may not be widely known that you can heat liquids above their boiling temperature. And if they're in a very smooth container and they're very pure liquids, then they won't boil right at the boiling temperature. You need starter bubbles for boiling to occur, because you need the pressure inside the bubble to be bigger than the exterior pressure of the liquid plus the surface tension of the bubble interface to be smaller than the pressure of the vapor inside the starter bubble. So what we see here, this is a very short video where liquid water has been heated in a microwave in a clean glass, and it's heated above 100 degrees C, and it's stable, but it's in a so-called meta-stable state. That means it's very easy to disrupt it and cause an explosive phase transition. So let's see what happens when we disturb it by dropping in a penny. Okay, so what you saw was that the liquid exploded into water vapor very quickly. I should note, by the way, this is extremely dangerous. I found this clip on YouTube. You should not try this at home. You can get third-degree burns from this very easily. So you shouldn't reproduce this at home. Okay, so we decided to base our particle detection technique on this phenomenon. So what are we looking for? As we said, we have the recoiling low-energy nucleus traveling through the superheated liquid, and occasionally the recoiling nucleus will deposit enough energy in a small enough volume of space that we will make a starter bubble that's big enough so that it grows spontaneously. So here is a room temperature superheated liquid, and we're shining a neutron source at it. And what we're going to see is a video that actually in reality was 1/10 of a second long, but it's slowed down so you can see it. So a single neutron comes in, hits a nucleus here, and then the liquid explosively transforms into a gas. Okay, so as I said, this entire sequence, when it reaches its end, is 1/10 of a second long. And clearly, this single neutron hitting a single nucleus keeps growing until we can easily see it with cameras. We can also hear this type of transition. So what does a bubble chamber look like? A bubble chamber has a liquid that's superheated. It's in a very smooth container that won't get that won't spontaneously allow the liquid to boil. We'll be looking at the liquid with cameras and listening to the liquid with acoustic sensors. And there's hydraulic fluid outside, so we can disrupt that explosive phase transition. So only a small amount of the liquid becomes a gas, and we can reset the detector fairly quickly. So this is a photograph of a single bubble that grew inside our one of our earlier chambers, a 2-liter bubble chamber. And you can see that we were easily able to see with our cameras the existence of the bubble. That camera then sent instructions to our pressure control unit, which slammed the pressure on into the hydraulic fluid, which crushed this bubble out of existence. Now, in addition to observing with cameras, we observe this with acoustic transducers. So this is when the bubble occurred, we could hear the sound on acoustic transducers that you can see at the top of this figure here. And we've used a variety of target fluids, which are chosen to search for various hypothesized types of WIMP dark matter particles. And then you might ask the question, why are we also looking with acoustic sensors? Why are we trying to hear that? It turns out in 2008, the acoustic transducers made by IU South Bend students were actually determined to be able to distinguish bubbles that were initiated by nuclear recoils, which is what we're looking for in the case of dark matter, and bubbles initiated by the radioactive decay of contaminants in the uranium and thorium chain. So, for example, here, what we have is a plot of data taken in a small chamber of the number of events on this axis, and on the horizontal axis is the loudness of the bubble, with greater loudness to the right. The data taken in black here is when we had a neutron calibration source exposed to our bubble chamber. The data in red was taken from searches for WIMPs, for dark matter, where it turns out we are dominated by radioactive decay. It even turns out that we're able to do measurements of the energy of the decays, and so we know exactly which radioactive decays occurred. So there's the radon alpha decay to polonium-218, the polonium-218 to lead-214, and the polonium-214 to lead-210. These are the alpha decays which initiate the growth of bubbles, and we could tell by timing that the higher energy decays corresponded to the louder bubbles. And so why is this important? Because it allows us on an event-by-event basis to discard radioactive background, which is our chief background in the experiment. Okay. We don't have to worry just about radioactive backgrounds. Cosmic rays are another potential problem for our technique. Cosmic rays are high energy particles coming from space, from events such as supernovas, and they slam into our upper atmosphere, creating a rain of subatomic particles that would go through our detectors if they were on the surface of the Earth. And so we have to bury our experiments deep underground in order that the ground absorbs these cosmic rays. So, for instance, at the Earth's surface, there's about 140 muons per square meter per second, while at the depth of our lab, Snow Lab, which is more than a mile deep, there's 100 million times fewer of these potential background particles. We also have to protect our detectors against radioactivity in the mine air and in the materials that the detectors are made out of. And in fact, that was one of my main responsibilities on a previous experiment that I worked on called the Sudbury Neutrino Observatory, where I was protecting the detector from radioactivity in the mine air and also measuring how much radioactivity got by all of our protection techniques. So our experiments are done deep underground, and this slide will give you just sort of a sense of what it's like to do this kind of work. In the winter, you come to the laboratory, and the temperature may be minus 40 degrees, and you get on a cage with miners at 6 in the morning. You go underground. We're at the 6,800 foot level, and you go through an active nickel copper mine. So there's blasting and dust, and you're walking about a mile to the lab. Once we get to the lab, though, we go through various stages of cleaning ourselves and anything we bring into the lab. And we enter the actual experimental halls area. And it is, in fact, the cleanest area in the universe in terms of radioactivity, except perhaps for laboratories on other planets where aliens are also doing astroparticle physics experiments. This is what one of the two types of detectors that we work on looks like. This is the so-called Pico 40 bubble chamber experiment that is a room temperature bubble chamber experiment. This is the inner vessel. This is where the superheated liquid would go. It's then put into a pressure vessel, and then that pressure vessel is put into a container. That the pressure vessel is put into a container that holds water shielding to protect us from neutrons coming from the rock walls. And we have 4 cameras looking in on this detector, and we are currently taking data with this detector. We're in the process now of constructing a ton scale version of this experiment. The construction is somewhat advanced, but we're still doing R&D until the last minute. So, for instance, IUSB fabricated the data acquisition systems for the acoustic transducers and built the acoustic transducers themselves. We're also responsible for the data acquisition system for fast pressurized transducers, which is a sort of backup technique that if the cameras fail, we can nevertheless stop the liquid from boiling by detecting a pressure rise in the detector. And we're also responsible for the data acquisition system for the 50 or so temperature sensors spread throughout the detector. But we are still doing some R&D, in particular on the electronics for our acoustic transducers. We're also participating in another experiment based on liquid argon. These types of bubble chambers are particularly good at looking for a slightly different type of dark matter candidate, but are also good for studying the properties of neutrinos. So currently we're building 2 of these 10 kilogram bubble chambers. One is going to go to the deep underground site at Snow Lab, and the other one is going to go to a power reactor studying neutrinos coming from that reactor. Here you can see those detectors under assembly. I do want to point out that PICO is an international collaboration with experimenters from around the world, and SBC, the liquid argon experiment, has collaborators from all 3 North American countries. And also we have IUSB students participating in this work as well. I also want to point out that along the way towards doing our basic science, all of our groups have developed new technology with real-world applications. And if anybody has any questions they want to ask me, please don't hesitate to contact me, at this email address. Thanks for your attention.